Yeah. So I'm giving this tutorial entitled Formal Languages and Neural Networks on Sequences. And I also kind of helped Ashish Sabharwal, my collaborator, helped me prepare this. So his name is here as well. And the focus of this tutorial is on neural networks and formal languages, but the motivation comes at least partially from natural language processing and the recent progress that's been made there. So in NLP, you may have heard about these language models that people have been building, which are basically these big neural networks that are trained just to predict the next word in some text. And people often talk about these language models as black boxes, so we don't really know what kind of representation of grammar or linguistic processing is going on inside them. But in fact, they do have a common structure. So nowadays, most language models are neural networks, and specifically, they're a type of neural network called the transformer, which was obviously mentioned in Dana's talk. And people train these models to just predict the next word. So for example, given Rabat is in, Morocco would be a natural continuation. But these systems can be used in lots of different ways to solve very general purpose problems. So the most basic use case you could do with a system like this is to just generate text. And if you play with ChatGPT, that's fundamentally what's going on. But also you could take the internal representations of these models and use them as kind of the building blocks towards solving lots of different NLP problems or problems in other domains even. So with that said, let me just move this. The goal of this talk is to understand the computational power of transformer neural networks. So two of the guiding questions I'm going to be focusing on, what are the kinds of computation that transformers are doing, and where does it fall in the Chomsky hierarchy? This is probably a natural question to people here who like to think about automata and other classes of language recognizers. And then another question is kind of a weaker form of that, which is what problems can transformers not solve? In other words, can we use theoretical analysis of the expressive power of transformers to come up with upper bounds on what transformers can do and find things that might cause these models to struggle? Because recently there's been a lot of progress in the field of natural language processing, and it'll be interesting to kind of figure out where this progress might fall short and what we might need to go further. So to motivate these questions, I'm also just going to show you a couple kind of empirical screenshots of playing with ChatGPT to show why I think these are important. So on the one hand, today's transformer language models are really impressive, and at first glance, it seems really kind of magical, and we'd like to understand how they work. So two examples of this, the thing I'm focusing on here is the fact that models don't just output text that is linguistically kind of syntactically correct, but also requires reasoning. So I asked ChatGPT to prove the Myhill and the Rode theorem for me, which is a classical result in formal language theory. And it gave me basically this correct proof of the theorem, which maybe 5 or 10 years ago, this would have been a crazy feat for a language model to do. So you might object that maybe this isn't actually that impressive because this is a theorem that's very common on the internet, and maybe the model has just been trained on data that contains tons of proofs of this theorem. So we can also come up with modified versions of this where we construct some new operation over languages, and we ask the model to prove that that the regular languages are closed under this operation. And even in this case, for this very kind of weird thing that has probably never been asked before, the model is able to give us the right answer. So that gives some evidence that the model is not just producing text that looks like coherent English, but in this case, it's actually doing something that constitutes at least like a basic form of reasoning. But of course, these language models aren't perfect reasoners. AI isn't solved, despite what you might read on the internet about neural networks or language models. And it's very easy to come up with similar looking prompts that trick the models and break down their reasoning capabilities, if we want to say that they have those. So for example, I asked ChatGPT again to prove that a to the n, b to the n cannot be recognized by a push-down automaton. And of course, a to the n, b to the n is a context-free language, so it can be recognized by a push-down automaton, but ChatGPT doesn't indicate this. Instead, it gives us a proof trying to justify this claim that is incorrect. And what's more concerning in this case is that not only does it give us the wrong answer, but it gives us a proof that might convince someone who doesn't really know too much about formal language theory. So for example, this proof is invoking the pumping lemma. It's kind of doing all the right things you might expect for a proof of this form, even though it's like wrong. And in the real world, this is how we get kind of news headlines like this. So there have been cases recently where, like in this case, a lawyer used ChatGPT to generate some text for a legal document in the US, and ChatGPT generated something that was basically nonsense or was citing kind of sources that didn't exist, and this lawyer got in a lot of trouble. So if people are going to use these language models in the real world, and there's this potential for reasoning failures that look convincing, it's important to understand, ideally, like when these failures are going to happen, or at least the types of problems that will induce them. And this is where kind of like upper bounds on what transformers can do really is like motivated. And also, another interesting related question is what kind of reasoning errors are kind of inherent to the transformer, or which errors might be happening just because our models aren't big enough. So with empirical experiments with transformers, you can see whether a specific model will fail on some kind of problem, but you can never guarantee that if you had just made the model bigger or changed the learning rate or some other parameter, that it wouldn't have succeeded. So theoretical results are much more definitive in this sense, and they give us the capability to say that, you know, some issue is not just a property of a specific model failing, but a more general kind of problem with the approach of large language models. So that brings me to the main results that I'm going to get to in this tutorial. So the main theme here, I think, is the expressive power of transformer models. So there are 4 parts, but the main results will come in part 2 and 3. So part 2, we'll be talking about transformers in terms of circuit complexity, and it will show that basically transformers can only recognize languages in this class called uniform TC0. And there are a couple interesting implications of this. So one is that transformers cannot recognize all of the regular languages. Another is that it gives us, by using kind of other results in complexity theory, we can get examples of problems that break transformers. So in other words, things that transformers can't do. And then in the next section, section 3 of the talk, I'm going to talk about extensions to the circuit complexity view. So how we can use these results to get a characterization in terms of logic of what transformers can and cannot do, as well as some analysis of decoder augmented transformers or chain of thought transformers. So here's the outline of the talk. So the motivation was kind of pitched around transformers, but I am also going to talk a little bit about RNNs, although I think Dana talked in more detail than I will get into about RNNs. But part 1 will be focused on RNNs, just to give some context for the transformer results. And then part 2 will present these circuit complexity results about transformers, so this upper bound that I mentioned. And then we will take maybe a 5 or 10 minute break so people can, go to the bathroom or whatever. And then I'll come back to 2 more sections. So one is the extension to these expressive power results about transformers. And then the 4th part will be just a brief section talking a little bit about learnability. So Dana pitched learnability as this kind of interesting open problem for neural network models. And I tend to agree with her. And I'm going to just talk a little bit about some recent work that I find interesting there. But again, more questions than answers. And I should say also that between these sections, I'll pause for questions. So because the sections are a little bit different in topic, if you have kind of a section that's relevant or a question that's relevant to that section, please feel free to ask when I'm done with the section. So that brings us to part 1, which will be about the expressive power of recurrent neural networks. And recurrent neural networks are perhaps the simplest model or neural network model that you could use to process a sequence. So the way they work is very analogous to finite automata. You basically have your input sequence, you encode each word with a vector, and then you also have a vector state that represents kind of the state of processing some prefix of the sequence. And in order to update this state, what you do is you compute a linear transformation followed by a certain nonlinear function to compute the next state as a function of the previous state and the current word. So for example, we start with a state that's the 0 vector, and then when we see the token rabat, we can compute our second state by updating our state, and we can continue this process until we get to the end of the sequence, at which point we can take the final state as a representation of the whole string and use it to predict the output. So if we're doing language modeling, the output here might be Morocco. So that's the standard RNN model that most people are familiar with. There's actually an older model of RNNs, which I'm going to call the non-real-time RNNs, that is similar, but kind of slightly generalized. And this is one of the models that was studied extensively in the 90s when people were trying to establish the expressive power of RNNs. And the key difference with this model compared to the more familiar model I showed on the last slide is that we can keep computing past the end of the input sequence. So even after we've read the last token, we can continue to update the state vector kind of until the model decides to halt. And at that point, we output some next token. So an important parameter in this model is going to be the data type. So in other words, we have these numbers in the vectors in the neural network, and we have to say kind of like how those numbers are represented, how much precision do they have, et cetera. And the three choices that are kind of natural here are binary, rational numbers, and real numbers. So the most general result we can have about these non-real-time RNNs is what happens if we give them real valued weights. And this was studied in 1994 by Hava Siegelman and Sontag. And it turns out that this is kind of, although this seems like a natural choice, right? Neural networks have kind of continuous representations of vectors in them. So real numbers seem like kind of an appropriate choice. It turns out to give a way too powerful characterization of their power. And the reason for this is that they basically recognize this complexity class called P/poly. And this is a class that contains some undecidable problems. So for example, variance of the halting problem would be in this class. So this maybe creates some cognitive dissonance because we know that computers shouldn't be able to solve undecidable problems. But the reason this holds is basically because having real valued weights in a neural network is way too strong, and it allows these degenerate constructions. So because real numbers can have infinite size, you can basically store an infinite table of lookups in your model, and you can do things that allow you to get beyond Turing machines. So the conclusion from this first result is basically that infinite precision weights, or in general, weights that are just super large infinite objects, is not a good way to analyze what these models can actually do, because in practice, we need to implement these on computers, and we need to use some kind of bounded precision. So we want to kind of refine this and somehow constrain the types of numbers that are allowed in the network to make the result more realistic. So a natural idea, and the one which Siegelman and Sontag went with, was what if we go from real numbers to rational numbers? Because of course, rational numbers always have a finite description. They don't have these kind of infinite repeating decimal points that real numbers have. Or they may have a repeating decimal point, but there's a fractional representation of that that's finite. So because we have a finite description, we're no longer going to be able to solve any undecidable problems. And maybe this is a better model that we can study to try to get a sense of what RNNs can do. So it turns out that if you make this, if you enforce this constraint that the weights have to be rational numbers, we get this reduced characterization on the right, where now suddenly these non-real-time rational RNNs are Turing complete, rather than being able to solve problems beyond Turing machines. And the way this works out is that we can simulate basically a two-stack Turing machine in the weights of the RNN. So we can use kind of a fractal encoding of a stack and simulate a stack with 3 neurons. And then once you have 2 stacks, there's a way to kind of represent a normal Turing machine with a single tape using those 2 stacks. So the details of this proof aren't too important for this talk, but the thing I want to stress about this is that even though we don't have infinite precision here, we're still relying on like kind of arbitrarily precise rational numbers because we're trying to fit a full Turing machine tape, which could be a super large data structure, into just 3 single neurons. And that's going to, again, cause problems in practice. So even though this model can't solve problems that are uncomputable, it still is not the most realistic model of RNNs in practice because it relies on this unbounded precision weights, and it also relies on unbounded runtime. So again, this is the non-real-time RNN model where we can continue to loop after reading the input rather than just having to output immediately after seeing the last input token. So that brings us to the third model studied classically by Siegelman and Sontag, which is RNNs with binary weights. And the result they had here is that this variant of RNNs are equivalent to automata. And the proof idea here is that only a finite number of possible hidden state vectors can fit inside the RNN because you only have 2 options for each neuron, either it's on or it's off. And they're not the first people to notice this correspondence between automata and RNNs. In fact, even when RNNs were motivated, even when automata were introduced originally, they were kind of a model of recurrent computation in the brain. So this is not a super surprising result. But the thing I do want to stress about it, well, also it applies with or without real time. So if you remove this infinite looping at the end, you don't reduce the power because it's still a finite state machine. And the thing I want to stress about it is that this is really the closest model to practical RNNs out of these 3 that I've talked about. So in the NLP literature, at least, people often cite this Turing completeness claim about RNNs, that if you make your model big enough, it'll be Turing complete. And that's just not quite true because the assumptions are off. So if we're trying to have a mental model of what RNNs can do, as Dana also was kind of alluding to, automata are really the best kind of first order approximation of their expressive power because real-time bounded precision RNNs are effectively automata. So I think I already kind of talked through the points on this slide, but the Turing completeness results that came out in the 90s for RNNs do not really describe RNNs as we typically think about them. They describe RNNs with unbounded precision and runtime, which are still an interesting model in their own right, but they're not what people use to process sequences in NLP. And empirically, if you test what networks can learn, they can't really reliably learn beyond regular languages. So Dana's already talked about some of the work that establishes this. I'm not going to go through it in detail here. But there are these extensions of normal RNNs. So far I've just talked about the most basic RNN variant, but there are other versions of RNNs called LSTMs or GRUs that you may have heard about, which have this more complex gating function. So rather than just computing a simple affine transformation to get the next hidden state from the previous one, they have these more complex gating. And a natural question that we can ask then is, how much more power do we get if we use something like an LSTM compared to just the basic RNN? Because in practice, the LSTMs work much better in various NLP applications. So that leads me to describing what LSTMs are. So I'm not going to give a formal definition, but I'll just show a little picture. So the key idea with an LSTM that goes beyond an RNN is that it has an additive update function. So rather than just computing the next hidden state as a function, as an affine transformation plus a nonlinearity of the previous state plus the current input, we're going to compute basically an update vector using that standard affine transformation mechanism, and then we're going to add that to the previous hidden state. So here, the previous hidden state is 0. We first compute an update vector, and then we add that update vector onto 0, rather than just setting the new hidden state to be the output. And the benefit here is that we no longer have kind of a compact domain for our hidden states. So we can potentially do some more complex sequence processing. Yeah, and in particular, one of the things we can do is counting. So this is a result shown by Gail Weiss et al. In their 2018 paper. which by this point I think is quite well known. So basically, they showed that you can use this kind of accounting mechanism inside the LSTM to recognize a non-regular language like A to the n, B to the n. So because normal RNNs are effectively automata, this is giving some additional power to the LSTM that normal RNNs would not have. And the way it works is that we can basically predict a +1 update for the A's and a -1 update for the B's. And because we can now add our update vector to the hidden state rather than just assigning a new value to the hidden state, we can kind of keep this running sum as we process the sequence and check whether it adds to 0 at the end. And we can accept the string if and only if we have a 0 and some other kind of finite state conditions about not seeing a B before an A will hold. And that will guarantee that we recognize exactly A to the n, B to the n. So an interesting thing here is that if you're familiar with kind of the standard, well, A to the n, B to the n is often discussed as a context-free language, and the construction for recognizing it with an automaton relies on using like a pushdown or a stack. But here we're actually not using any kind of stack data structure. We're using a counter data structure where we're just adding 1 and minusing 1 rather than pushing A and popping when we see a B. So this is a different construction, though kind of similar in spirit to the classical stack-based one. And it shows that A to the n, B to the n is actually kind of not just a context-free language, but also a counter language. And that was the construction to give kind of an intuition about how it works. But one of the cool things that this Vice et al. Paper showed was that not only is this something that is possible in theory, but it also gets learned in practice. So if you take an LSTM and you train it on long strings of the form A to the n, B to the n, or on short strings and then test it on longer strings, you get this pattern in the hidden state vector that corresponds exactly to counting. So what this graph shows is basically the value of the hidden neuron as a function of the number of tokens that it's processed. So about halfway through the string, we switch from A's to B's. And you can see that for the first half of A's, we're adding 1 to the state for each token. And then when we start to see B's, we're subtracting 1. So this individual neuron in the network is really capturing the exactly what the theoretical construction was doing. It's adding 1 for an A or adding some number for an A and then subtracting that same number for a B. And we can also make the contrast against a normal RNN, or in this case, a GRU, which is another extension of a normal RNN, but kind of similar to a normal RNN. And in that case, because the network doesn't have this counting capability, we get a very chaotic hidden state update sequence. So it seems like counting here is being realized, and it's kind of a key capability that LSTMs have and other RNN variants do not. So we can also ask about where this counting capability puts us in the Chomsky hierarchy or in relation to other types of RNNs. So remember that the kind of vanilla RNNs are roughly finite state. And then if we have these non-real-time rational RNNs, we get Turing machines, which is like the highest level of the Chomsky hierarchy. And then in between, we can consider some of the other classes. So the context-free languages and the context-sensitive languages. And it turns out that because of this counting capability, LSTMs end up with this characterization. So they are contained within context-sensitive, but they cross-cut against context-free. And this is because they basically resemble counter automata. And there's a lot more that can be said here. So there's kind of more fine-grained comparison of different variants of RNNs. There's other models of LSTMs that are, there are other variants of LSTMs that have like more or less power. So there's a couple papers on this. For example, this one that Gail Weiss and I wrote together in 2020. But I'm not going to really focus on that here because I think the focus for my talk is going to be transformers instead. So I think these RNN results give some nice context for thinking about transformers because they show us a couple things. One is that counting seems like a useful capability for a neural network to use to process sequences. Another thing that we learned from looking at RNNs is that it's really important how you set up assumptions about precision if you want to get meaningful theoretical results. So if you allow the models too much precision, you end up with a theoretical model that doesn't reflect practice and where you can kind of get Turing completeness or some other kind of universality result like that in a way that isn't actually realistic. So when we go to transformers, we're going to kind of try to use these insights there to get a kind of sufficiently constrained model of what they can do. Okay, but before that, I'm going to stop briefly. If there are any questions about RNNs, happy to take them now.
Hello. Yeah, just one question I've had about this in general, both during your talk, but also like many other times I've seen this discussed. Do you have any comments on like the complexity of the number of samples that's required with respect to say like the length of like the types of sequences you're presenting? The reason I'm asking this question is because I'm oftentimes thinking about this in the context of like child language acquisition, right? Mm-hmm. And things like, you know, arguments from the poverty of the stimulus. So I'm always interested in hearing not necessarily identification in the limit, but also just like what happens when you have a very limited set of samples, and how does that like learnability scale?
Yeah, that's a great question. So I guess my focus here is more on expressive power. So kind of like if you could design the weights by hand, what types of things could you do rather than like practical learnability? And I think I don't have any great answers there. I think kind of like Dana was saying, thinking about learnability is a hard problem, and we don't have like great guarantees about, you know, to say how many samples something will require or not. I guess one exception is this sparse parity task that Dana mentioned, where there are lower bounds that seem to correspond to what neural networks actually achieve. There is a lot of empirical study of like sample complexity with neural networks though. So for example, there's right now a challenge called Baby LM, which is training language models on like realistic amounts of child-directed speech, kind of trying to get at this language acquisition question that you mentioned. So I think if you look more at empirical results with models trained on varying amounts of data, you can see that there are some answers there, although I'm not sure exactly what's the most relevant to you.
Thank you.
So I have a question regarding your, so I'm wondering what's your take on Dana's feasible learning of RNN on regular languages. It seems to me that she doesn't believe that RNNs can learn regular languages easily in practical sense. But you propose that RNNs, simple RNNs can exactly learn regular language, and as LSTMs can learn more than regular languages. At least that's from this slide and from some of your papers that I've read. So what's your take on Dana's feasible learning of RNNs in previous talk?
Yeah, that's a good question. So to clarify, this plot is about expressive power. So this talk is just kind of nothing about learning, nothing about what models can do from data, but just kind of if we can design the weights however we want, what are the limits on what the models can do? That's the way to interpret it. So it's kind of an upper bound on what models can learn. I totally agree with Dana that it seems like lots of different regular languages are not feasible to learn. Like parity, for example, is very difficult to learn with neural networks. And yeah, I think the question she pitched is a super interesting one, which I will have some thoughts on in the last section of the tutorial, which is kind of aimed more at learnability, whereas the first three sections are going to be more about expressive power.
Was another question around here?
Yeah, apologies for my stupid question. I'm new to this field, but these counting systems, Because it seems to me like the example you give, it just counts the number of A's and counts the number of B's. But can you count something more difficult, like count whether a certain subword occurs and you don't know beforehand what the subword is?
Yeah, that's a good question. So you definitely can count more abstract things. Definitely in transformers, I'd have to think a little bit about LSTMs, but for exactly what, but you could, for example, count the number of occurrences of bigrams or the number of positions where some other count was equal to zero. So kind of a second order count where you're not just counting the first quantity, but you're using another count to achieve some other count. And yeah, I think there's a surprising amount that you can do in terms of counting. So for example, you can also, in transformers or in a near variant of transformers, there's a construction to recognize Dyke languages using only counting. By counting basically occurrences of parentheses and figuring out which parentheses match other ones and so on. So there's more you can do besides counting just individual tokens.
Another question?
Okay, so I will continue onto transformers. So before talking about transformers and introducing the architecture, I want to just motivate a little bit where they came from, because they do look quite different to RNNs, but they kind of developed out of RNNs in some sense. And the exact progression was first people had RNNs, then introduced in the context of machine translation, this kind of extension called attention that improves RNNs. And then finally, it was proposed that we could kind of do away with the recurrent part of RNNs and just use attention to process sequences. And that's kind of where transformers came from. So RNNs with attention are this extension of the normal RNN where you get this ability to look back at previous hidden states. So, okay, well, I think it's mostly clear. Let's say we're processing Rabat is in, and then we want to predict the next word, Morocco. One useful capability here, especially on long sequences, might be to look back over the previous hidden states and see whether any state encoded like the name of a place. Because in is kind of giving us a cue that we want to predict a place, but maybe our current hidden state has forgotten in some sense what the place we're in is. So if we can look back at the previous sequence and see that there was another place name that occurred, this might be useful to inform our prediction. So attention is kind of a soft mechanism that allows us to do that. So it lets us take a weighted average of the previous hidden states. And the way that we decide which ones to kind of put more weight on is by doing a kind of key value lookup. So we can use our current hidden state and look for like some other hidden state that maybe contains the right kind of information that our current hidden state is searching for. This is very kind of hand wavy, but I'm not going to go too much into the formal definition here. But the crucial thing here is that we have this block, which I'm going to call an attention mechanism, that takes a weighted average of the previous hidden states, and then sums the hidden states kind of according to their weights, and then that allows us to get our final prediction, rather than just using the final hidden state directly. And transformers take this one step further. The paper that introduced transformers was titled "Attention is All You Need," which is somewhat self-explanatory. Basically, the idea is we can get rid of the recurrent part of the RNN and just use these attention mechanisms as the only way that we look across the sequence. And then we also are going to add these feed-forward neural networks, which you can think about as just simple local functions that can just map the vector from one word to a new vector, but they can't kind of look at other words. And we're going to interweave these two different types of layers to process the sequence. And this transformer model is because of this quite different than, at first glance at least, from automata, because you don't have, and even in like the simplest automata, you have kind of this left to right structure where you process the sentence one word at a time. But here, the way that we process sequential structure is by taking lots of different weighted averages and using the information that comes out of those weighted averages to inform the final prediction. So on the last slide, I showed a transformer as a language model, which is, again, how these are often used in the real world. but we can equivalently think about them as language recognizers if we basically ask the transformer to predict yes or no at the end of a string. And in this case, we just get kind of a standard model that defines a class of formal languages, which is the set of strings where the model outputs accept or yes. So with that, we can think about where these transformers fall in the Chomsky hierarchy. And here's the picture that I showed you before from RNNs. Unfortunately, it's pretty hard to place transformers in the Chomsky hierarchy. And as you'll see by the end of the talk, actually, it's probably not possible because transformers are incomparable with a lot of these classes. So that presents a problem, right? If we want to think about the power of these models, how can we do that if we can't use the Chomsky hierarchy? So the problem, just to make it explicit, is that there's no recurrent structure in the transformer. So this means relating the transformer to an automaton of some kind is difficult, right? If we want to try to, the normal way you would try to establish a relationship between two models is to simulate one with the other. But because the structure of the models looks very different, directly simulating a transformer with an automaton or vice versa is a hard problem. So instead, we need to come up with a different set of tools to use to think about their expressive power. And what's turned out to be a useful viewpoint is circuit complexity. Or in other words, viewing transformers as circuits and placing them into hierarchies of problems defined in terms of circuits, rather than placing them into the Chomsky hierarchy. And the intuition for this is that both transformers and circuits are doing this kind of parallel computation over sequences, rather than processing the sequence left to right, one token at a time. And because circuits are going to be relevant for this analysis of transformers, and because it's also maybe a somewhat obscure subfield of computer science that people aren't familiar with, I'm going to give a brief tutorial now about circuit complexity and how it's relevant for transformers. So circuits are a model of computation that take inputs and give you an output. And crucially, they can do this with parallelism, which is kind of one of the things that differentiates them from Turing machines or other models of computation. And formally, what they are is a directed acyclic computation graph, like shown here on the left. And the input nodes represent bits typically, although it's not too hard to generalize them to take elements of a formal language, or like elements of an alphabet for a formal language. And the internal nodes are logical functions like and, or not. And then finally, the output node that we get is a 0 or a 1. And the way we get it is by basically just feeding the inputs through this computation graph and seeing what the output evaluates to. So for example, we could, to evaluate on 0, 1, 1, we first assign 0, 1, 1 to these like input nodes in the graph. Then we can compute the depth 1 nodes by just taking the inputs they receive and computing the corresponding logical function. And then once we have the depth 1 nodes, we can compute the depth 2 nodes. And in this case, we call this the output of the circuit because it's the final bit that gets produced. So that's what a circuit is. There's kind of two natural complexity measures for circuits. So one is the circuit size, which is simply the number of non-input nodes in the circuit graph. So here the size would be 3. And the interpretation of circuit size is that it kind of captures the runtime of the circuit if you wanted to run it without any parallelism. So if you wanted to, for example, compute the output of the circuit on your computer in Python without taking advantage of multiple processes or something, you would have to kind of iterate over all the nodes and evaluate them. And this would correspond to like 3 different steps. So the number of steps is just the size of the circuit. The other complexity measure that's relevant here is the circuit depth, which is basically the length of the longest path from the input to the output in the circuit. So here the depth is 2. We have a couple different paths of length 2. And the interpretation or the motivation for this complexity measure is basically telling us the runtime of the circuit if we had optimal parallelism. If we could kind of do everything all at once the minute it became available, the minute its inputs were defined. So this is kind of like how we executed the circuit 2 slides ago when I showed you this example. We could execute all the nodes at depth 1, then all the nodes at depth 2, and so on. and the total runtime would just be the depth of the circuit. So those are circuits. Circuits can be thought of as functions from a fixed size input to 0 or 1. So they don't quite define an infinite formal language because there's like a certain input size that each circuit is associated with. But there's a natural generalization of this called a circuit family, which does give us a formal language. And the way it works is we basically have a sequence of circuits corresponding to different input sizes. And when we want to check whether a string of size n is in our language, we use circuit n to compute yes or no. So for example, if we have a string of size 1, we have a circuit C1 that we can use to get a 0 or 1, telling us whether this is a valid string. If we have a string of size 2, we could use circuit 2, and so on for larger values of n. So now our kind of model of a formal language is a circuit family, which is a sequence of circuits. And there's something a little bit strange about this definition, which is that these circuit families can be what's called non-uniform. So non-uniformity means that the circuit can change kind of arbitrarily with the input size. So if we go back to the last slide, you see that I have 3 completely different circuits here, and there's no constraint that they kind of look similar in any way. And this actually allows circuit families to solve some undecidable problems, similarly to real valued RNNs. And the reason for this is because the description of the computational model is kind of infinite size, right? There's this infinite sequence of circuits, and infinite size models are the ones that are capable of doing potentially undecidable things. So it turns out that this is not really an issue for now. So even though circuit families can do undecidable things, they also are quite constrained in other ways. So we can still use them as an upper bound on transformers. But later in the talk, I'm going to come back to this point, and I'm going to fix it by enforcing what's called uniformity. So informally, what uniformity says is that the circuits for different input sizes cannot be too different from one another. And I just wanted to kind of flag this here so that when I come back to it, it will be somewhat familiar. So that brings us to the first kind of class of circuit families or problems defined by circuit families that is worth considering for thinking about transformers, which is called AC0. And this is the set of problems that can be recognized by constant depth poly-size circuit families. And one way to interpret this is that AC0 corresponds to problems that can be parallelized to a very high degree. In other words, to constant depth. So there's some kind of circuit that solves this problem with parallelism really fast, no matter how large the input to the circuit is. And to see how this falls out of the formal definition, polynomial size here means that the number of nodes in the circuit is basically a polynomial of the input sequence length. So there's potentially a lot of different computations happening in the circuit, but the key thing is that it's constant depth. So that means that the number of steps, the number of steps, if we're executing the circuit in parallel, is bounded no matter how large, no matter how large the input sequence gets. So fundamentally what we're doing is this kind of very shallow, but potentially very wide computation. So because of this parallelism, AC0 you should think about as a very limited complexity class. So the types of formal languages here in AC0 typically are quite weak. So there's this kind of classical result in circuit complexity establishing lower bounds on circuit depth for certain problems, which means that parity, for example, is outside of AC0. So this is the problem that Dana talked about, which is computing basically the XOR of a sequence of bits. So for example, it works this way. And then another problem that is outside AC0 is this other simple language called majority. So majority is basically taking the majority vote of a sequence of bits. So for example, if I give you a 110, this would be in majority because there's 2 1s and 1 0. But if I had instead given you 1 0 0, this would not be in majority because there's more zeros than 1s. And majority is kind of intuitively very simple. It's a language that is not quite regular, but it's not too hard to see how you would solve it with counting, going beyond regular languages. And parity is, of course, a regular language. So what we see from this is that there are regular languages that AC0 does not contain. So that brings us to the first result I'm mentioning about transformers, which is that we can basically simulate hard attention transformers in this very simple class AC0. And this is a result from Yiding Hao, Dana Anglin, and Bob Frank. So what they showed is basically that hard attention transformers can only recognize languages in AC0. And what hard attention here means is that when we take these weighted averages in the transformer, we have to put all of the weight on a single token. So rather than taking a true weighted average, we're basically making a hard choice to retrieve one specific token when we look back. So this is a simplification of the transformer that is necessary to get this result. So what does this result tell us? Well, it basically shows that hard attention transformers are a quite weak model in terms of the formal languages they can recognize, because they can't recognize parity, majority, or any of the other simple languages that fall outside of AC0. And because parity is a regular language, again, this tells us that hard attention transformers cannot recognize all regular languages. But of course, I've already alluded to the fact that hard attention is a strong simplifying assumption. Because we can't take true weighted averages like a normal transformer can, we have to kind of look at one thing and retrieve that from the context in the attention heads. And this is particularly a problem because we know that transformers use soft attention to count or kind of compute these kind of like almost sums like LSTMs. So this is an empirical result from Badam Mishra. And in particular, this counting capability that transformers have via soft attention can allow them to recognize majority. So this is going to kind of show us that with soft attention, the AC0 upper bound doesn't hold because we have an example of something outside AC0 that the transformer can do if we give it kind of the full power of attention. And I'm going to walk through this in a little more detail now. So how could we recognize majority with the soft attention transformer? As a reminder, majority is this language where we want to compute basically the majority vote of a sequence of bits, which is not in AC0. And let's say we get the input 110. The way we do this is by simply taking a uniform average over these bits. So in this case, this would give us the value 2/3. And then we can use the feed-forward network in the transformer. Recall that the transformer has this kind of alternation of attention with feed-forward networks. So we can use a feed-forward network to just check whether this average token is greater than or equal to 1/2. And this will exactly recognize majority because if more than half the input bits are 1, we will get a 1 here. And if less than half are 1, we'll get a 0. So this shows us that soft attention adds power compared to the hard attention upper bound. But the question is how much? And specifically, can we establish kind of a slightly generalized upper bound, which is still meaningful, but also holds for soft attention transformers? So that brings me to the next kind of result about transformers, which is this non-uniform upper bound for soft attention transformers. And specifically, we're going to be talking about, well, because we're now talking about soft attention, where we're taking averages in the transformer, we need to be a little bit precise about the precision that we're computing these averages in, right? So for RNNs, we saw that precision was important. If you wanted to think about expressive power, and if you had too much precision, you would get kind of a vacuously strong like result about expressive power. So for analyzing transformers, what we're going to assume is basically log precision. So what that means is that if we're processing an input of length n, the precision we get to use for computing averages is logarithmic in n or less. And the reason for this is because log precision allows us to maintain information about position. So we can, for example, store pointers to different positions in the sequence, but it's not too powerful. And there's more kind of theoretical and empirical arguments in favor of this that I'm not going to get into here. But for now, I just want to point out that all these results from now on are mostly going to be talking about log precision transformers. So here's the first upper bound result for log precision transformers. So this is from a 2022 paper of ours, where we basically extended the hard attention upper bound to show that log precision transformers can be simulated by polynomial size, constant depth, threshold circuit families. So another way to say this before I define what a threshold circuit is that these transformers can only recognize languages in the class called TC0. And then what a threshold circuit is a simple generalization of a normal circuit where basically in addition to and, or, and not, you also get this third primitive gate called majority, or called MAJ, and MAJ just computes majority. So if you remember from before, majority was this simple problem that was outside of AC0, but we can take AC0 circuits and we can extend them with majority as a primitive, and then that's going to give us like a strictly more powerful minimal generalization of AC0. And that class is going to be called TC0. So analogously to AC0, TC0 is polynomial size, constant depth, threshold circuits. And again, we know for free that TC0 contains AC0, and it's also strictly more powerful because we know you can compute majority with like a trivial TC0 circuit. So here's, I'm going to go through the proof of this theorem just at a high level. So the idea here is basically that we want to simulate each transformer component in TC0. And by that, I mean we want to construct a TC0 component or circuit that computes an attention mechanism and computes a feed-forward neural network. And because transformers, roughly speaking, are just a composition of attention heads and feed-forward networks, this tells us that the whole network, if we compose everything together, will also be in TC0. So to simulate the attention component, recall that attention is basically just a weighted average of some previously defined vectors in the network. And classically, we know that summation and division are problems that can be solved in TC0. And a weighted average is really just taking division to compute some coefficients and then taking a sum of those coefficients multiplied by some vectors. So it follows fairly straightforwardly from that attention can be computed by a TC0 circuit. And then for the second part, we want to show that these feed-forward neural networks are in TC0 as well. So the property we're going to use here is that these networks take just a single vector as input rather than a sequence of vectors. And we can use this lemma from Howe et al. That says that basically any Boolean function of C log n bits is in AC0 and hence is also in TC0. So combining these two results, we basically can conclude that the whole transformer will be in TC0 as well, although I'm skipping over kind of the details of stringing that together. So what does this result mean, or what does it tell us about kind of what transformers are capable of? Well, one kind of straightforward interpretation is that transformers can only solve problems that can be parallelized to a very high degree. So like AC0, TC0 is this class that is defined around a parallelism constraint where the depth of the circuit has to be constant rather than depending on the input length. But of course, it tells us that like while the computation graph can be parallelized, it kind of assumes that you have majority or counting as a primitive, right? So because we have these majority gates, which can do some kind of counting inside the network architecture, inside the definition of TC0, we can only parallelize transformer computation if we can also kind of do counting or taking majority votes as a primitive part of the computation graph. And this is interesting because it suggests maybe some kind of parallel between LSTMs and RNNs, where we saw that what LSTMs could do over normal RNNs was counting. Similarly, with transformers, soft attention seems to give some kind of counting capability that hard attention transformers don't have. So that's kind of the intuition for why we need this TC0 upper bound for soft attention, but AC0 was enough just for the hard attention transformers. Now, a nice thing we would like from this upper bound is concrete examples of things the transformers can't do. So if you remember like the motivation for the tutorial, that was one of the kind of practically motivated problems here. Unfortunately, with the current TC0 upper bound, we don't really get that because this is non-uniform TC0. But the next section, or the next subsection of this transformer section, is going to be showing how we can refine this upper bound to get a uniform TC0 upper bound. And this actually allows us to kind of place transformers in hierarchies of problems in complexity theory and get clear examples of things that they cannot do. So yeah, the game here is basically going to be trying to refine the upper bound I showed you before to be uniform. And the goal of that is to, again, find some concrete things that transformers are going to struggle with. So what uniform means, basically, is that the intuition I gave earlier is that the circuits for different input sizes in the circuit family aren't too different. But formally, what uniformity says is that the circuits for different input sizes can be constructed by a resource-bounded Turing machine as a function of the input size encoded in unary. So the notion of uniformity I'm mainly going to be talking about is log space uniformity, which means that the Turing machine gets log space in the input sequence length when it constructs the circuit to run on inputs of size n. And this is all a bit abstract, and it's okay if you don't follow the definition of uniformity, but the reason why we need to do this is basically because we get really nice properties for uniform circuit families where they fall into like other conventional complexity classes. So no longer can these uniform circuit families do undecidable problems, and furthermore, they kind of form natural subclasses of like log space, L, or polynomial time, P. And yeah, and then I guess the other class in this hierarchy that I haven't mentioned is NC1, which is another circuit class that's kind of intermediate between L and TC0, which will come up again later. And the result we're going to show is this one. So we're going to show that log precision transformers are not just in TC0, but also in this uniform TC0 class, which places them nicely in this hierarchy. And once we have this result, we can use what we know about the upper levels of this hierarchy and the problems that are like complete for those levels of the hierarchy to find things that transformers can't do. So first, I'm going to talk about how we can strengthen the result to go through in the uniform case. So here's the uniform statement of the same theorem I showed you before. Basically, the only difference here is we're saying that to simulate a transformer, you can do this with a log space uniform threshold circuit rather than an arbitrary threshold circuit. And what this means kind of naturally is that transformers are in the log space uniform variant of TC0. And this maybe shouldn't be too surprising at an intuitive level. So uniformity says that basically the processing that happens for different input lengths is not too different. And if we think about a transformer, because the parameters are shared across columns in the network, really the same computation is happening and being naturally unrolled no matter how many inputs you give the transformer. So in other words, to build a transformer that like goes from n to n+1 tokens, all we have to do is just copy the nth column onto the n+1st token, and the transformer will kind of naturally generalize. At least, like in practice, transformers might not learn to generalize to higher lengths, but in theory, their computation graph is capable of doing that. So it's not too difficult to see, or hopefully that gives some intuition for why transformers are going to be in uniform TC0 and not just normal TC0. And to go through this a little bit more formally, we can go back to the same proof from before, where I was talking about how to simulate the different components in the transformer with threshold circuits. And we can just consider what happens if we want to prove the stronger claim that you can simulate each component with a uniform TC0 circuit. So for the attention mechanism, everything goes through kind of the same because this fact that summation and division are in TC0 also goes through for uniform TC0. In the feed-forward case, we need to be a little bit more careful So last time we relied on this lemma about kind of universal, that you can universally compute any function if it has a small enough number of inputs with an AC0 circuit. But here we need to add this additional constraint that the function we want to compute is computable in basically C log n space. And this is for technical reasons, but this condition is satisfied for neural network components. So that's okay. And everything goes through here as well. So that's a bit about the proof. And now we can think about the implications of this result. So the first one I want to talk about is what this tells us about how transformers and automata are related. And basically the conclusion we get here is that they're likely incomparable. And what likely means is like assuming some conjectures in complexity theory that no one has been able to prove do hold, then they are incomparable. So specifically, the reason we know this is that transformers can clearly recognize non-regular languages. So I showed you before how they can recognize majority, which is a counting language. And in the other direction, transformers can't recognize all regular languages unless TC0 equals NC1. In other words, these two levels in the hierarchy collapse. And the reason for this is because there's a problem, which is the word problem for permutation group 5, which is both known to be regular and NC1 complete. So what that means is that this complete problem separates TC0 from NC1 unless those classes collapse. And if those classes collapse, that means this language is both regular, or if these classes do not collapse, then we get this region in NC1 that contains some regular languages, but we know that the TC0 can't solve problems that are outside TC0. And I gave you kind of like the witnesses in either direction for this claim, but I think there's a more intuitive way to say this, or there's an intuitive interpretation of this result, which is that some automata are just too recurrent for transformers to compute because transformers need to have this constant depth computation graph. So this S5 language I mentioned is basically a canonical example of something that is fundamentally recurrent and requires you to kind of incrementally update your state. And any NC1 complete regular language would also kind of satisfy that property. Whereas like transformers, because they're constant depth, can't do that kind of simulation of recurrence. So that's the first like major implication I wanted to highlight from this result. The second one is kind of how we can use this to come up with examples of problems that transformers can't do. So if we just think about these upper levels of the circuit complexity hierarchy, we can find complete problems for those classes, similarly to how S5 was complete for NC1. And we can conclude that basically, unless the hierarchy collapses, these are problems transformers can't do. So there's a lot of different languages you could write down on this slide. You could basically just use lists of complete problems from like a complexity theory reference. But some of the ones I wanted to highlight include Boolean formula evaluation, which is an NC1 complete problem. So this would be taking a Boolean formula as input and trying to give back true or false for what it evaluates to. Another one is linear programming, or even more specifically, solving a single linear inequality or linear equality. So if you have an equality like AX equals B and you have the matrix A and the vector B, can you find an X to decide whether this is true or false for some X? So like a satisfiability question. And this is a polynomial time complete problem. So unless TC0 and polynomial time collapse, which seems quite unlikely, transformers shouldn't be able to do this kind of linear inequality solving. Another P-complete problem is horn satisfiability. So this is a like constrained version of SAT, which you may have heard of, that's more tractable. And then also the universal context-free recognition problem. So this is the problem where you get as input both a context-free grammar and a string, and you want to say for any context-free grammar in any string, does that grammar generate that string? And this problem also turns out to be P-complete. The other level of this hierarchy that's interesting is L, which is log space. And there's natural, very fundamental, complete problems for L, such as graph connectivity. So undirected graph connectivity is basically checking in an undirected graph whether there's like a path of edges between two nodes, and the directed variant is the same thing if you have directions on the edges. And these turn out to be L and NL complete respectively. So NL is just the non-deterministic variant of L. And these are very like natural search problems for like a lot of AI applications. So it's, as you'll see in a second, it's easy to like encode kind of real world problems as graph connectivity. And the fact that transformers can't do this suggests kind of like a clear limitation on what they can do. Another one I threw here is primality testing, which is not known to be complete for any of these classes, but intuitively, it seems like one of the harder problems in P. So as long as it's not an L, for example, this would also be something that transformers shouldn't be able to do. And I'm also going to focus now for a bit on these last two problems because I also have some empirical results showing that transformers can't really solve these problems. So the specific experimental setup is we took ChatGPT and GPT-4, which are like probably the two of the best transformer language models available. And we asked them to basically solve primality testing and graph connectivity problems. You can ignore this third senator search one, which is less formally interesting. And what we found is that the error rate of these very large, generally impressive transformers on these problems was very high. So for GPT-3, it was around 70%, and for GPT-4, which is supposed to be like the newer, better model, it's about 80%. And, or sorry, for graph connectivity, it's 80%, and then for GPT-4, both of those numbers go up. That's what I meant to say. And moreover, so it's maybe not too surprising that in practice, transformers can't solve these problems that we proved they shouldn't be able to solve. But one of the things we found that was maybe more unexpected is that not only do the transformers give you the wrong answer, but they generate kind of an explanation for that wrong answer that contains some invalid reasoning. So for example, for a primality testing problem, let's say we ask ChatGPT, is 9677 a prime number? We first get a wrong answer. No, 96677 is not a prime number. But then the model also gives us an explanation of why this is true, even though it's wrong. 9677 is prime, just to clarify. So it gives us a factorization of 9677 that it claims is correct, but this is actually not a valid factorization. And furthermore, if we take this factorization, then we just ask ChatGPT about it in a separate session, it will very reliably know that this is incorrect. So it seems like the fact that we're giving ChatGPT a hard problem and it gives us a wrong answer and then kind of post hoc has to justify that answer is what's causing it to give us this wrong factorization. It's not that ChatGPT doesn't know how to factor 9677 or doesn't know how to verify factorizations of 9677. It's that like we asked it to solve a hard problem and it committed to an answer and had to come up with some kind of justification for that. So this was an interesting finding, and it seems like it might connect to this like hallucinated proof that I showed you at the beginning of the talk, where ChatGPT not only was like kind of tried to prove something that was unprovable, but actually gave us a proof that looked correct by like invoking the right kind of theorems, but in the wrong way. So that's the end of this section. I guess to complement the RNN results, the main transformer result that I've talked about so far is that in terms of expressive power, transformers recognize languages in this complexity class called uniform TC0. And the two like most interesting takeaways from this is one, this means that they can't recognize all regular languages, and moreover, they're incomparable with the regular languages, so they can do some, some non-regular things, but they also can't do all regular things. And then the second thing was I showed you how we can use this circuit hierarchy to find examples of problems that transformers can't do. And a very natural one that jumped out was graph connectivity, because this is like a very fundamental problem that comes up in a lot of like real world reasoning contexts. So I'll pause again for questions. Water.
Thank you so far for the interesting talk. My question was, you showed some results for the recurrent neural networks, and then you showed some results for the transformer. And in between, you motivated it with the recurrent neural network with attention. And kind of the proof for the transformer was going via attention and what this could do, and the proof for the recurrent neural network was using this recurrent capabilities. So I wonder, from a theoretical perspective, is recurrent neural networks with attention more powerful? And do you know any results about this?
Yeah, that's a great question. The short answer is yes, they are more powerful. So I will get to some, in the next section, I'll get to some results that aren't exactly like recurrent neural networks with attention, but they're showing how adding some kind of recurrence to transformers can actually make them more powerful and able to recognize all regular languages. So I guess the reason why in practice people don't use that is because having recurrent neural networks with attention is like slower to train compared to just training a transformer. So while you do kind of gain in expressive power, you lose in the ability to train these models really quickly. So yeah.
Okay, thank you.
I see Jeff has a question online. Jeff, if you can unmute yourself, I think you can ask.
Yeah, thank you. This is really interesting, and I have just a clarification question about the family of circuits. So I really, this has confused me a long time, but I think you really helped me understand this better. So when you talk about a uniform circuit complexity, that essentially means that this family of circuits is computable in the sense that there's a computable function from a natural number n to a circuit. And that's the first part. And the second part of the question is you also mentioned the resource bounding on that. And so where the computable function has to be bounded in, I think you used log space in your discussion. So when you talk about a uniform, TC0, for example, what exactly is the resource bound that's on that computable function for the circuit families? Thanks.
Thanks for the question. Can you say the last part again? I didn't quite catch the last sentence.
Oh, the last part is just exactly what it means when we talk about a uniform constant depth poly-size threshold circuit, or just uniform constant depth poly-size circuit. That means the circuit is poly-size in the size of the number n. That's the input to the computable function.
Yeah, exactly. So for the first part, you're exactly right that basically any uniform circuit family is going to be computable because you can just compose the Turing machine that builds the computation graph with actually executing the computation graph. And then as far as why we impose these resources and constraints, it's because we don't want too much of the computation to be going on inside the Turing machine, but we want to make sure the circuit is still like doing enough. And then, yes, so the size and depth constraints, they apply as a function of n, which is the number of like tokens in the input, the number of bits in the input. And the log space is also defined in terms of, I guess, the number n, or you could think about it as the size of the string 1 to the n.
Okay, thanks a lot.
Other question? Yes, the last question before the break.
Well, I want to ask about an application of transformers. I'm working on a project on NER, named entity recognition. I wanted to ask what is the most powerful kind of models? Are transformers better than simple RNNs or LSTMs? If transformers are better, which one is the better one? Hard attention or soft attention?
Yeah, thanks for the question. So based on these results, like soft attention is definitely more powerful than hard attention. I guess in terms of comparing RNNs to transformers, like one implication of this regular language result, the fact that transformers are incomparable with the regular languages, suggests that they're also incomparable with RNNs. So there's kind of some things RNNs can do that transformers can't do and vice versa. So I guess we don't know exactly about how LSTMs and transformers relate, but it seems like there are some similarities in what they can do. So they can both simulate counting, which seems to be useful. And I think that's one reason why both models are very strong, because counting is like a good capability to have in a model. Oh, that's, yeah. I guess another advantage, so we don't know exactly how they relate, but one advantage that transformers do have over LSTMs is that you can potentially train them at scale much easier. So if you're working in a small scale regime, it might be worth trying both if you can like afford to train both of them. But if you have tons and tons of data, then transformers become much easier to work with.
Good. So thank you, Will. I think we will now take a little break, a short break. Let's say we come back here at 5. So it's like a little bit before 5 p.m. now. So we come back here at 5 p.m. and 5 minutes, which is roughly in 8 minutes. So start your counters. Thank you, everyone. Yep. Well, to make people come back. So welcome back, everyone. We'll now start with the second part of Will's tutorial.
Okay. Ready to go? Okay.
Okay, perfect.
All right.
Back to you, Will. Thanks.
Okay. So now that we're back from the break, I'm going to move on to part 3, which is similar to part 2. Part 2 is mostly focused on this TC0 upper bound and some of the implications of that. But this is going to be about extensions to that picture. So ways that we can take the circuit complexity analysis and then gain new insight in terms of logic and algebraic characterizations of transformers. And then I'm also going to talk about the power of transformers with a decoder, or equivalently what I'm calling chain of thought transformers. So the first part of this section is going to be about logic. So I'm briefly going to introduce just logics over strings and why I think they're interesting for thinking about neural networks. So logical sentences can be used to define lots of different types of objects, but one application is sets of strings or formal languages. And the way this works is we can write down constraints that we want a set of strings to satisfy using a certain logic. So for example, if we want to specify the set of strings that contain the bigram AB, we could write there exists an index I such that A occurs at I and B occurs at I plus 1. So that's kind of how this notation is working here. And this particular logical sentence, I'm going to call first order because it can quantify over positions in the string, like this existential quantifier with I, but it can't quantify over like sets of positions or kind of more higher order things. So that's why it's first order. And this is an interesting, from a formal language point of view, this is an interesting kind of logic and class defined by logic, because a particular variant of this first order logic class actually is equivalent to the star-free regular languages through this classical result of McNaughton and Papert, which some people may be familiar with. So I think in general, using logics to define set of strings is like an interesting way of doing things because it's very interpretable, and you can read off the logic kind of like what the constraints are that declare this set of strings. And there's also nice correspondences between at least some logical classes of languages and kind of like classes of languages defined by automata. So a natural question then is, can we capture transformers with some type of string logic? You know, it seems like we're not going to be able to capture them with automata because they're incomparable to automata, but maybe there's some type of logic that describes exactly what transformers do, just like there's a kind of logic that describes what automata can do. And we do obtain in a result in this direction, falling out of the TC0 upper bound. So specifically what we can show is that any language recognized by a log precision transformer can be defined in first order logic with majority. So this is an extension of the normal first order logic formalism. And I'm gonna, again, just illustrate how this extension works by example. So the key difference here, there are some other minor differences, but the key difference is that we are allowing a majority quantifier in addition to standard first order quantifiers. So if we want to use this majority quantifier to define the language A to the n, B to the n, the way we could do this is we could say that most of the tokens are A. So that's the first clause in this formula, the mi A of I thing. We could also say that most of the tokens are B, which is the second clause. And together, these are going to imply that basically half the tokens are A and half the tokens are B. And then we can add a third standard first order clause that doesn't use any majority quantifiers to enforce that the bigram BA does not occur anywhere. So by defining A to the n, B to the n this way, we have this like nice, very compact definition of A to the n, B to the n. And it's expressed in first order logic with majority. And just to go back to the result I mentioned, what we proved is that anything that transformer can do can be written in this logic, just like we've written A to the n, B to the n in this logic. So where does this result come from? It seems like last section I was talking all about circuits, and now we're talking about logic. So how did this happen? Well, in the paper that I cited for the result, what we basically did was we strengthened this TC0 upper bound for transformers. So that upper bound was for this log space uniform notion of TC0. But it turns out if you make TC0 more uniform, so if you go to log time uniformity instead of log space uniformity, that actually TC0 is equivalent to first order logic with majority. So circuit families that are sufficiently uniform are just equivalent to like logics over strings. And we can use this to get an upper bound on the type of logic that you need to simulate a transformer. So that's an upper bound, this first order logic plus majority. It turns out that concurrent work to us was also considering the other direction. So in other words, what if a logic where if you can define a string in that, or define a language in that logic, it means that transformers can recognize that language. And what they showed, this is, the first author is David Chang, and then he has a couple other co-authors whose names I'm forgetting at the moment. But what they showed is that any language definable in this logic they call FOC plus mod, which is basically accounting logic with plus and mod, can be recognized by a transformer. So I'm not going to go into too much detail about how their logic is defined, but the takeaway here is that we get a picture like this. So if we want to think about what logic is necessary and sufficient for describing a transformer, we get this kind of sandwiching picture where on one direction, we know that anything you can define in this FOC logic can be simulated by a transformer. And similarly, anything a transformer can do can be simulated by FOM. And then furthermore, we know that FOC plus mod is a proper subset of FOM. And there's also specific problems that seem to separate these other edges. So FOC plus mod cannot do a to the n, b to the n, but via the construction I kind of alluded to in the last slide, with counting, transformers can recognize a to the n, b to the n. So it seems like there's some potential to improve this lower bound to be tighter, closer to transformers. And on the upper bound side, it seems like there's some capabilities that transformers do not have, which can be expressed in FOM. So one of them is kind of arbitrarily nested quantifiers. Rather than just quantifying there exists I, saying something like there exists I, j, and k, such that some property holds. So I think it's a very interesting open question on the kind of logical expressiveness side to try to refine these results and say, can we kind of sandwich both of these bounds together to get like a tight characterization that gives us exactly what transformers can do as a logic. And then in order to reason about the power of transformers, we could instead just reason in terms of this logic and be able to have good intuitions about the capabilities of transformers. It may not be possible to get a fully exact characterization, but I think even still tightening these results would be really cool. So that's how we can make a connection between logic and transformers using these circuit complexity results. Another viewpoint that has appeared recently is an algebraic one. And this really relates to trying to see how transformers relate to the regular languages. So I mentioned before that we have this incomparability picture where like there are some regular languages that transformers can't recognize and vice versa, but can we actually characterize the ones that transformers can't do? And this paper by Liu et al., which is called Transformers Learn Shortcuts to Automata, has some really nice insights about this. And there's a lot of things going on in that paper, but the part that I'm going to talk about here is this notion of solvability of the syntactic monoid and how this relates to what transformers can do. So to do that, I'm first going to define the syntactic monoid of an automaton. Let's say we have this automaton here, very simple. We can think about each word or each token in this alphabet as having a transition function induced by the automaton. So the transition function is just how this token affects the state of the automaton. So for example, the transition function for A would take Q0 to Q1 because that's what the transitions that are defined by A in the graph. And conversely, a B would take Q1 to Q0 because that's the transitions for B that occur in the graph. And then we can also think about the transitions for larger strings. So like AB, for example, would take Q0 to Q0 because any loop of AB starting in Q0 would end up back in Q0. So it turns out that these transition functions, basically we can think about each like string in sigma as giving us like a function, and they form what's called the syntactic monoid under function composition. So if you want to get the transition function for AB, you can just compose the function for A and the function for B. And this is a monoid because it's an algebraic structure that is associative and has an identity element, which is the empty string. So that's the syntactic monoid. Now we can talk about this algebraic property called solvability, which turns out to be important here. So a solvable group is a group that can be constructed from abelian groups via group extension. And a solvable monoid is a monoid where all subgroups are solvable. I put these definitions here, but I don't think they're super relevant and they're kind of abstract and tedious. The intuition that I want to highlight here is solvability is this property that says that a monoid or a group is kind of almost commutative. So in general, groups don't have to, these syntactic monoids don't have to be commutative. They just have to be associative. But if they are solvable, it means you can kind of view them as a commutative group plus something a little bit extra. And there's a rich theory for kind of decomposing and simplifying solvable semigroups or monoids into commutative operations, which is called Krohn-Rhodes theory, that is going to be used here in order to talk about transformers. So the result that Liu et al. Have, which I'm going to highlight, is that transformers can't simulate automata with non-solvable syntactic monoids. And the reason for this intuitively, well, connecting back to the circuit complexity view, is that the word problem for a non-solvable monoid is NC1 complete, or for an automaton with a non-solvable monoid. So kind of just like this S5 language we saw earlier in the last section is kind of inherently recurrent and can't be decomposed with constant depth. The same is true for any non-solvable monoid. So when you lack commutativity, or you're not even close to being commutative, it's hard to do that kind of computation with constant depth. And conversely, Liu et al. Consider the other direction. So what happens if we have a group that we know is solvable? Can we guarantee that there exists a transformer that can, if we have a syntactic monoid that we know is solvable, can we guarantee that there exists a transformer that simulates the corresponding automaton? And what they show is that if we kind of cheat just a little bit, so if we allow the width of the transformer to grow with the sequence length, then we can simulate the transition sequence for any automaton with a solvable syntactic monoid. So this is a bit of a generous assumption. Typically, the width of the network and the parameters have to be fixed with respect to the sequence length. But if you want to fix like a maximum sequence length, which can be quite large, the width of your network only has to be linear in that quantity. And the nice thing about this result in complement to the previous one is that it shows that this solvability criterion is like almost bidirectional in describing whether we can simulate any given DFA. So that's solvability. And the last thing I want to talk about in this extension section is what happens for transformers with chain of thought, or equivalently transformers that are allowed to have a recurrent decoder. And this is kind of a summary of some preliminary results that we hope to publish by like the end of the summer, hopefully. So chain of thought is this extension of normal transformers that allows you to generate tokens before answering. And this has been, this is not an extension to the model, it's just a new way of kind of using the model after it's been trained. And the idea is that in complex reasoning questions like, is Rabat in Africa? We might want to first do some intermediate reasoning. So for example, we could generate Morocco in Africa. And then once we've generated these tokens, it's easier to answer the question yes, because we can just verify that like Rabat is in Morocco. So empirically, this is a paradigm that has been used to take pre-trained language models and kind of prompt them to be better at answering reasoning questions. And this instance of chain of thought, I'm going to refer to as 3 steps because we're generating 3 tokens before giving the final answer. And it turns out that from a theoretical point of view, this chain of thought procedure basically naturally transcends the TC0 upper bound. And the reason for this is because you can consider this edge that's being added here when you generate Morocco and then add that back as input to the model to be creating some kind of recurrence. So TC0 was kind of defined by constant depth / lacking recurrence, and chain of thought is adding recurrence. So it seems like we might get some power beyond TC0, but it's kind of an open question. How much power does TC0 give you? with T of n steps. So you can vary how many steps you have, and you can ask how much more additional power do you receive. Oops. So the first result I want to point out is that with a linear number of steps, so if you're allowed to generate a linear number of tokens before giving the final answer, and this is kind of equivalent in some sense to maybe having a decoder in your RNN with recurrent connections, or in your transformer, then you can recognize all regular languages. And the idea we're going to use to prove this is that you can basically simulate a DFA directly where you write out the current state to the chain of thought. So back to this automaton from before, here's how this would work. So let's say we have the input AB. We can first write out the initial state to our chain of thought. And then we can use another step of processing to look back and find the first token and compute the transition function of the initial state and the first token. And then, we can repeat this process. Now that we have the second state, we can attend to the second token, and we can compute the transition function of the second state and second token, and so on. So if you repeat this process, you can basically simulate the state transition sequence of the DFA. And then with one additional step beyond that, you can just look at the final state that was generated and say whether or not it was an accepting state. So this shows us that chain of thought adds power beyond TC0 because basically we have recurrent connections in the computation graph. And actually we can extend this construction rather than just simulating a DFA, we can simulate a 2-counter automaton, which turns out to be Turing complete. So you might look at this and say, oh, does that mean that chain of thought transformers are Turing complete? Not exactly, because these 2-counter automata are Turing complete if you give them unbounded runtime. So if we care about staying within T of n steps of chain of thought, these 2-counter automata are super slow at simulating Turing machines. They can incur exponential blow up in the number of steps they need. So you can't really simulate an arbitrary Turing machine. You can simulate very simple Turing machines for a small number of steps, or an arbitrary Turing machine for a small number of steps. So that was maybe a bit confusing, but it seems like we're not going to be Turing complete with chain of thought. So instead, we might want to try to come up with some other upper bounds. So can we describe as a function of the number of steps that you're allowed, what types of problems you can solve? And the general upper bound we have here is that transformers with T of n chain of thought steps are in the space complexity class T of n plus log n. And this kind of comes out of the TC0 results for transformers without chain of thought. So that's like an intermediate step being used to prove this theorem. And I'm going to just walk through some specific applications of this. So this is like a general result, but the baseline we can compare against is kind of like transformers with no chain of thought, which is like in TC0. And then if we allow logarithmic number of steps, transformers will transcend TC0, but they remain in this complexity class L, which is log space. And if you remember from the previous section, this is the class of problems that contains graph connectivity and things like that. So possibly these types of transformers could recognize or learn graph connectivity, although we haven't tested that. And finally, we can also consider what happens if you have a linear number of steps. And in this case, we get as an upper bound the context-sensitive languages for chain of thought. So this bound could probably be tightened. Context-sensitive is quite a large class, but because the context-sensitive languages can be defined as the problems that can be solved in a linear amount of space, we get this result from the main theorem. So where does this square with the previous section? I guess there's 3 different things I talked about as extensions of the circuit complexity view. So one is porting these results onto logic. And I showed that basically we have upper and lower bounds on the logic you need to define transformers. So the lower bound is a logic where anything that can be defined in that logic can be recognized by some transformer, and the upper bound is a logic where anything a transformer can do can be written in that logic. And it seems like there's some opportunity to kind of tighten the gap between those two. And then the second thing I brought up was this property of solvability, which seems like a useful property for thinking about which automata can be simulated by transformers and vice versa. And then finally, I talked about chain of thought and how chain of thought, in a sense, does add substantial power to transformers in terms of expressive power. But does this mean that actually like transformers can learn things outside TC0 in practice? Not quite, because there's this, if we think about learnability here, transformers are never kind of trained to use a chain of thought. They're always trained to just predict the next token without any intermediate chain of thought. So when we use these transformers at inference time with chain of thought, in principle, that allows them to have this greater expressive power, but they have kind of no reason to have learned how to do that. So any like expressive power they gain kind of has to be by accident. So I think reconciling this and trying to figure out in practice, like what can transformers feasibly use their chain of thought to accomplish is like an interesting open question. And also just refining the analysis of chain of thought transformers. So I'll stop again for questions.
Yes, a question about solvable automata. How much are they limited?
Sorry, could you say the solvable automata?
What is the limit? Can they cope with many natural things, or what are the limitations of this kind of languages?
Someone might know better than me, but I believe that there's a correspondence between solvable automata and star-free automata. So I think that solvable automata are equivalent to star-free or something like that. Maybe I could be wrong, but they are going to lack no, that is incorrect. Well, basically the thing that solvable automata don't have is like counting modulo n. So if you can choose like parity for example contains counting modulo 2, and this makes it yeah, actually I'm not sure. You can check the paper. Yeah.
Any other question? Or someone knows the answer, but I don't know it either. Like the solvability, it's quite technical. This notion of I dig into this paper and it's yeah, it's tricky.
Yeah.
Any other question? No. So let's continue with.
Sorry, it's a naive question, but how do you implement the chain of thought in practice?
In practice?
Yeah, because you have to have several steps.
Yeah.
But is it bounded? Or how do you deal with that? And how do you implement that in real computers?
Yeah, so you basically fix a number of steps. But in practice, what people do is they take a model that hasn't been trained to necessarily explicitly reason with a chain of thought, but they just say at the beginning of the question, like, let's think step by step about this. Like, it sounds like a joke, but that is, people just add that string at the beginning. And then it can encourage the model to produce a chain of steps before giving you the final answer. So I guess that kind of gets back to what I mean about, like, it's unclear whether and how transformers would be able to use this additional expressive power if they don't get to use a chain of thought during training time. Like, they don't get to make a hard decision about the next token and then condition on what they generated at train time, because that's not differentiable and it doesn't like work with how we optimize neural networks. But people just kind of use this hack afterwards, after the model's been trained. And it's possible that the solution the model found could just magically use the chain of thought in an interesting way to get more power, but it's not clear that that's what's happening in practice.
So as a follow-up, I have a question. Like in this chain of thought, you don't fine-tune the model, but then you kind of tune the classifier at the end? Or is there any training that is happening in this?
So there are probably ways you could fine-tune the model to be better chain of thought, but the minimal setup is you have no fine-tuning at all. You just use it to generate tokens, and your output is just what it generates after it's done its chain of thought, and you take like the last couple tokens as the output.
Okay.
Yeah.
There's no other question. Yeah, let's continue with the next part.
Sounds good. Okay. So that brings me to the last part of the talk. So far I focused on expressive power of RNNs and transformers, but now getting back a bit to Dana's topic, I'm gonna talk about learning biases of transformers. And I think in the results I've been showing you, there's like an emerging picture and some nice theory about the expressive power of transformers, but in contrast, the learning biases or the feasible learnability, however you want to describe it, is much harder to make theoretical claims about. So why do we care about learnability? Well, again, the past sections have focused mainly on expressive power. And when we think about expressive power, upper bounds are quite informative. So if we can prove that something can't be expressed in a model, that means that it also can't be learned. At least it can't be learned perfectly. But in the other direction, just because we show that there's a construction where chain of thought transformers can simulate automata, or we can learn parity in a normal transformer, or we can represent parity in a normal transformer, that doesn't mean that these things can actually be learned from data in practice. And especially, and by in practice, I mean like with gradient descent or with the types of algorithms that people use in deep learning. So in order to make kind of claims with predictive power in the other direction about what transformers can actually do in the lower bound direction, rather than what they can't do, we need to think about learnability and like what is the right model of like feasible learnability, or what are properties of some problem that make it learnable or unlearnable by an RNN or by a transformer. So I'm going to talk about two different like learning biases of transformers in this section. And by learning bias, I mean a certain type of property or like that transformers are likely to draw from their data. So the first one is this notion of sensitivity. And sensitivity is a complexity measure. And it's been shown in some empirical work that transformers seem to be biased to learning low sensitivity functions. And I think there are potentially, one of the connections here between sensitivity and the circuit complexity stuff is that sensitivity is a complexity measure for Boolean functions, and circuits are a model of computation over Boolean functions. So there seems to be maybe something that could be connected between these two points of view. And the other thing I'm going to talk about is this notion of norm growth, which is a kind of phenomenon that happens to a transformer while it's training, and the effect that this has on what the model learns. So specifically, that it seems to cause neural networks in general to learn sparse functions, and in the case of a transformer, it seems to kind of simplify the types of attention that the transformer can learn to be more sparse. Okay. So for the first one, I'm going to talk about sensitivity, and let's first define what this sensitivity complexity measure is. So sensitivity is a fairly robust measure of complexity for Boolean functions of a finite input size. So if we have a function 0, 0, 1 to the n to 0, 1, we can talk about its sensitivity. And by robust, what I mean is that it's polynomially related to many other notions of complexity for these types of functions. And this is implied by the sensitivity conjecture, which is no longer a conjecture, but was proven a couple years ago. So the way we define sensitivity is at a specific input is the number of input bits that can be flipped to change the output. And I'll go through a couple examples of this in a second, but that's this kind of local measure of sensitivity with respect to a specific input. And then we can talk about the average sensitivity, which is just the average of this complexity measure across all the different inputs in the domain. So for example, let's think about the sensitivity of the binary AND function. So sensitivity of AND at the input 0, 1 is just 1. And the reason for this is because we can flip the first bit and change the output. But if we flip the second bit, it doesn't have an effect. So we have a sensitivity of 1. And maybe you can think to yourselves for a second about the sensitivity of 0, 0 and 1, 1. And I'll show you the answer. So in this case, the sensitivity at 0, 0 is just 0 because no matter if you flip the first bit to a 1 or the second bit to a 1, you still, AND would still return false on that input. And at 1, 1, the sensitivity is 2 because in this case, either bit, when you flip it, you would kind of cross the decision boundary for the output of AND. So this means that the average sensitivity of AND is just 1 because if we add up all of these sensitivities and divide by the number of inputs, we get 1. So another example of a Boolean function that we can measure the sensitivity for is parity. And basically because any individual bit will change the output of parity if you flip it in isolation, the sensitivity of parity is n, which is the maximal value. And this is also the average sensitivity because it doesn't matter which input you give, this will hold. So from this point of view, parity is like a very complex or highly sensitive function. So maybe you can already see why like sensitivity might be a good hypothesis for like a measure of like difficulty for learning because as Dana mentioned, parity is one of these functions that it's really hard to get a transformer or even potentially an RNN to learn. So that brings me to the empirical results about this. So these two papers have shown that basically LSTMs and transformers both seem to have a bias for low sensitivity functions. And some of the ways that they measure this are as follows. So they looked at these models at initialization. So when you haven't trained them at all and just they kind of are a random function. And they looked at kind of the distribution of sensitivity for these random functions and found that it was very concentrated over low sensitivity for both LSTMs and transformers. And after training on some random Boolean functions, you can also look at how the sensitivity of the model compares against the sensitivity of the process that generated the training data. And again, what both these papers have found there is that the sensitivity of the trained model is lower than the true sensitivity of the process generating the training data. So in some sense, when you just have a data set, a finite data set, the sensitivity is underspecified because you don't get to observe all the like neighbors of points in the data set. So the model has to draw some generalization from that data set about what the true sensitivity is. And a way to interpret these results is that it seems to be biased towards generalizing in a low sensitivity way, even if the true generative process was high sensitivity. And another result from these papers is that transformers actually seem to have a stronger low sensitivity bias than LSTMs do. So the second paper from Bada Mishra compared the distribution of sensitivities in both of these settings, I believe, for transformers and LSTMs, and the transformers seem to be like much more concentrated at low sensitivity. I should also mention, although it's not super relevant here, because I guess we're interested in neural networks over sequences, but you can also look at the sensitivity of a feed-forward neural network that's just taking a fixed size input and there are kind of older results showing that these feed-forward neural networks are also biased towards low sensitivity. So given that, it maybe shouldn't be too surprising that we also get this bias at the level of neural networks on sequences. So that's the first learning bias of transformers and also, I guess, LSTMs that I wanted to highlight. But the second thing I'm going to talk about is this notion of norm growth and how it induces saturation or kind of simplification of the attention in transformers. So I guess Dana already showed a plot like this, or maybe not this exact plot, but one thing you can do is you can take a function that we think is going to be hard for a transformer to learn, like a sparse parity function, and you can train the model on some data from that function and see whether it learns correctly and how long it takes. So we did that in this paper, and we got this plot. So this is kind of replicating findings that are maybe expected, but an interesting thing that happens here is that the model initially overfits. And by overfits, I mean it gets good performance on the training set, the examples that it's seen, the blue line, but it doesn't generalize correctly to new strings that weren't included in the training set. So that's the orange line. You can see that by 10 epochs about, that's how the model is doing. But then if we train for more time, there's this point where all of a sudden, without seeing any new data, so here, 1 epoch is 1 run through the complete data set. And even though we haven't seen any new data at 100 epochs, suddenly the model starts to generalize correctly. And this is really surprising. If you think about the conventional machine learning wisdom, where like, if you train for longer with a neural network, it's gonna like memorize the data and it might overfit. But here we're seeing kind of eventually the opposite pattern, where just training longer and not seeing any new data is actually causing the model to generalize appropriately. So this phenomenon has been referred to as grokking in the recent literature. And basically the key idea here is you have like a memorization phase where the model initially memorizes the training set on some hard function like parity. But then if you train long enough on the same data without showing any new examples, the model suddenly jumps to a solution that generalizes. In other words, it computes the right function rather than just memorizing the data. And this is, again, really confusing, so it'd be nice to get some clarification about why this happens and what about the neural network training is causing this generalization out of nowhere. So we asked this question in this recent workshop paper. And we basically wanted to look at the internal state of the model and see what was changing during and around the grokking point. So is there some like property of the weights in the model that can kind of explain why you see this change in the behavior? And what we found is that grokking coincides with rapid norm growth. And by norm growth, I mean all of the different parameters in the network, or not all of them, but a select subset of the parameters in the network are growing larger, while the other networks are kind of shrinking at the same rate. And this norm growth actually induces basically some sparsity. So it causes a subnetwork to control the prediction of the output rather than having all the neurons in the network have an effect. And this seems to be a useful kind of bias, having a sparse network for computing a sparse parity. So I'll show you this plot now to kind of make this point more quantitatively. So the way to read this on the left is I'm plotting the norm of the weights. So basically just the magnitude of the weights, but it's the L2 norm. There's kind of two groups here. So there's like the red weights, which are this like subnetwork that is growing in norm. And then there's everything else, which is like the yellow or blue lines, which are kind of two controls that represent the rest of the network. And you can see that right before we see this grokking transition on the right, where the network starts to give us the right answer, the norm of the subnetwork starts to grow, and then it kind of accelerates and grows rapidly until we've crossed the grokking threshold. So until we are kind of giving giving the right answer and generalizing correctly. So it seems like this norm growth is probably like very related to what's happening. And the fact that the subnetwork is kind of separating from the other weights and starting to dominate the computation of the network is what's maybe causing, or at least is related to the grokking like generalization performance gain that we see. So that's in this like very toy setting of feed-forward neural networks trained on sparse parity, but we can also look at the norm of the weights in an actual like large transformer language model. So this plot is showing the norm of the weights for T5, which is a large language model trained several years ago. And what you can see is that the norm consistently grows over time. So in contrast to before I was showing these two different groups of weights, and that there was like one group that was growing and one group that was shrinking. Here we don't get that level of information because this is an aggregate measure across the whole network. But my hunch here, and this has been corroborated kind of with other models in later work, is that the norm growth is actually focused at a specific subset of the weights. So even though here we see it as this kind of uniform trend, there's probably some of the weights that are getting most of the growth in magnitude, and other weights might be staying the same or shrinking, or maybe growing at a less rapid rate. And so this is like maybe the same phenomenon as what we saw in the small network, but is it going to have a similar effect? So before, in the parity task, it seemed like norm growth was useful because it gave the model a bias towards sparsity, but it's not clear exactly what the analog is going to be in a transformer. So what we found is that when you have this norm growth in a transformer, basically it causes the attention patterns to be either hard or uniform. And hard is the same kind of notion of hard attention I showed you in section 2, where all of the weight has to be on like one position when you attend back. And uniform would be the opposite of that. So basically that you're spreading the weight uniformly across all different positions. And here's just a picture of that in a transformer that we trained. So this is plotting basically a histogram of the different number of positions that are attended to by each attention head. And you can see that we get this very clear bimodal pattern where some of the weights are doing roughly hard attention. So they're attending to either one or a small number of things. And then we get this other mode of weights that are attending uniformly across the entire sequence. So it seems like there's really this like bipartite thing going on where either you do hard attention or you do uniform attention as an attention head. And as far as why this is the case, there's this theory of like saturated networks that I have worked on in the past. And it turns out that like saturated networks are kind of an approximation of networks with infinite norm. So if you have norm growth consistently during training, you're probably going to approximate these saturated networks. And this is like the type of attention, or at least a subset of the kind of attention that we would expect in saturated networks. So it's showing maybe that there's a correspondence. If we get norm growth during training, we're going to like consistently better approximate a saturated network as we train for more and more time. So that motivates this open question, I think, which is the power of saturated attention and how it compares against general soft attention. So I showed you this purple upper bound in section 2, where we get containment in TC0 from soft attention, but it's open. I mean, okay, so that is true. And then saturated attention is roughly hard attention plus uniform attention, plus some other options, which we didn't see realized in the plot from the last slide. But we can analyze saturated attention and show that basically saturated attention is also in TC0, just like soft attention. But it's unclear to what degree these classes are related to one another. And like specifically, is saturated attention a special case of soft attention? And is there some kind of important capability that separates them? So I think answering this would be interesting because it seems like in practice, transformers have a bias towards the saturated attention. So if we can show that that in some sense simplifies their hypothesis class or constrains them against learning certain behaviors, that would like suggest that, you know, we can kind of describe something about what can feasibly be learned by transformers in practice. So yeah, this question of a separation, I think, is an interesting open question. And then just to summarize the section a little bit, I guess there's two things I brought up. So one was sensitivity and the fact that transformers are biased to low sensitivity functions. And then the second kind of bias of transformers trained by gradient descent seems to be towards saturation. And here we have an understanding of the mechanism where it seems to be related to norm growth and the fact that the weights are going to grow over time, which kind of saturates the attention distributions. And the new takeaway that we get from the section is basically that transformers, have these biases, and in contrast to the previous three sections, this is really a claim about what transformers can learn, not about what they can express. So that's the end of section 4. I'm briefly going to just give some high-level conclusions, and then we can take questions again. So I think the two themes that I touched on in this talk are, one, transformers' learning biases, and two, their limits just in terms of expressive power. So part 4 was isolated in the sense that it was focused on learning. And the motivation for thinking about learning is really that, just because you can construct a transformer that does something doesn't mean that in practice, if we train a model on data, that it will acquire that behavior. And then part 2 and 3 were focused more on expressive power. And in particular for expressive power, I think some of the most informative results are the upper bounds. So when we can say that a model can't express a certain type of behavior, that also implies that the model can't learn that behavior from data. And I think there's been lots of recent progress on the expressive power of transformers. And I think this like circuit complexity view, which was originally introduced by Sophie Howe, Dana, and Bob Frank, has turned out to be very fruitful for understanding what they can do. And there's also a lot of rich connections that we can make from these results to different areas of theoretical CS. So I mentioned this logical characterization of transformers, and also kind of how we can connect it to like algebraic perspectives on automata. And So with that in mind, I just wanted to go through kind of the different results from all these sections again and how they fit together. So in terms of expressive power, we first talked about RNNs. And I think the general takeaway for thinking about the expressive power of RNNs is that depending on the type of RNN, they can either recognize the regular or languages or some class of counter languages if they have the right kind of gating mechanism. And then transformers don't neatly compare to the regular languages, but instead we get this upper bound of uniform PC0. And it does seem like uniform PC0 contains some things involving counting. So transformers can count just like LSTMs can, at least with soft attention, even though with hard attention, they don't seem to be able to count. And also we were able to come up with problems that transformers can't do using this upper bound by leveraging known results in complexity theory. And then finally, or additionally, I talked about how this circuit complexity view can be extended in terms of logic. So we can make the results more uniform and then kind of automatically gain a characterization of transformers, or at least an upper bound on transformers in terms of logic. And I think I'm optimistic that we can kind of push this logical perspective and maybe gain some kind of tighter characterization of what transformers can do in terms of logics over strings. And the other extensions I talked about in this section were solvability and how this can be used to describe the automata that transformers can and cannot recognize. And then also how we can also analyze chain of thought as this mechanism that potentially adds power to transformers, although it's unclear how and if transformers can learn to use a chain of thought during training time. And then finally, I gave you this last section about learnability. And I think there's a lot of interesting open questions around learnability. The two recent findings that I highlighted were about this kind of low sensitivity bias in transformers and norm growth and saturation. But I think, Dana also was talking about different aspects of what is learnable by RNNs. And I think there could be a similar research program undertaken for transformers as well. So yeah, that's the end of my talk. I'm happy to take more questions, and thank you for your attention. Okay.
There is another one here that maybe works. Thank you, Will, for this excellent tutorial. Are there any questions in the audience? Yes. This one is working. Ça va.
Just a very quick question. So I'm curious about like how do you do chain of thoughts on formal language experiments? Like what kind of prompts you use?
Yeah. So we don't have any experiments. I guess this section is just about this like formal model where you're allowed to generate tokens and condition on them before giving an output. So if I go back to the picture real quick, we're not saying that the model can learn to do something like this, but in principle, if you could like hand construct the weights, the model would be able to simulate this behavior where you write out the current state and kind of take that as the next input, and then you gain some kind of recurrence through that. But there's no prompting or like training going on here. Yeah.
So it's more like a theoretical discussion, right?
Yeah, yeah.
Okay, I was just wondering how chain of thought can be applied to formal experiments.
Yeah, I should say that in this empirical paper I mentioned for
the Zhang et al.
The
right?
snowball paper.
Yeah,
Yeah,
I read that paper as well. And
yeah,
yes.
so there we did find that you could use chain of thought potentially to do better at like graph connectivity and problems like this, although I don't think it was a perfect solution. I don't remember exactly the details. But I guess, yeah, it's always tough to say what the right prompt is for chain of thought, but I think the best strategy is to try a bunch and see what works.
Right. Yeah. And especially what do you do with like formal language experiment? Because you are not going to train like very huge models on formal language tasks, right? It's just small model and small parameter size. So it's not like, the ChatGPT that we've seen,
right,
which has humongous amount of parameters and data. It's not something that we can do with formal language experiments.
Yeah.
Thanks.
Thank you for a very nice talk. Just a little question about, you said that transformer cannot solve graph connectivity.
Mm-hmm.
What if we succeed to include attention mechanism in the graph nodes?
I see. So like a graph neural network is like one. So you're proposing an architecture that operates directly on a graph as opposed to on a string. Is that correct? Yeah.
Like aggregation between nodes or importance of some nodes, the same mechanism in the graph.
Yeah.
Can we solve the problem like this?
That's a good question. So I believe there's a type of neural network called the graph neural network, which is similar to what you're describing. And there's a recent paper that I believe shows that these graph neural networks are also in uniform TC0. So we have the same upper bound for that type of neural network as for a transformer. So that suggests that probably they can't solve graph connectivity. I'm not super familiar with the details of that paper, but like, unless there's something strange about the setup, I think that that would follow.
Thank you.
Yeah.
We have a question from Dana online.
Yes, thanks. Will, it's wonderful tutorial. Thanks very much for putting in all this work on this and explaining it to us. I haven't thought at all really about chain of thought. I had a question about how many computational steps are involved when you fix the number of steps after the input.
How many computational steps? So what do you mean by a computational step?
So we're on the slide, which is great. So you have your input and then you start generating further tokens and paying attention to them and other things. And eventually you stop and produce an output. You bound the length of this, the number of tokens that you're going to produce in addition. But what does that mean about the amount of time to compute the output?
I see. Well, I mean, I guess in terms of runtime, like if you assume that one step of the transformer can be computed in linear time, because you just have to compute attention over everything that exists already, then the whole thing is roughly quadratic. I mean, that's kind of like a known claim about transformers, that you have roughly quadratic time. I'm not sure if that gets at your question. I guess, yeah.
So I'm curious about how you get a space characterization.
Okay, where the result comes from. Yeah. So we use the fact that a single step here can be computed in TC0, which means it can also be computed in log space. And that's where space complexity gets into it. So if I go back to you can see that roughly what we're doing is T of n steps plus log n overhead. So this falls out if you just worry about how to like link up the different TC0 circuits together in the right way.
So in this case, if T of n is linear,
yeah,
we're talking about linear space, right?
Exactly, as an upper bound, but I think presumably it could be, you could say something tighter than that, but with our current technique, we can't.
So it would be linear space and quadratic time, actually.
Right, yeah.
I see what I was thinking about. Thanks very much.
Another question? Actually, I had one quick regarding, so for the bias towards low sensitive function, is it only empirical evidence that we have now, or do we have some theoretical understanding as well? Like, you know, you have this result for feed-forward neural network. You can actually show what happens during gradient descent, some kind of, you know, going through the low norm solutions, or like these behaviors, like learning one at a time, singular values, this kind of lowering thing. So how far are we in these directions?
That's a great question. I don't think we have any theoretical understanding, at least I don't. One potential connection is the statistical query learning results, which Dana mentioned. So I could see there being a connection where like learning by statistical queries, like learning higher sensitivity functions is harder by statistical queries. And possibly you could use these statistical query lower bounds to try to describe like how much time you need to learn a function of a certain sensitivity. But I don't think these results exist. It seems like there could be a potential connection.
It's interesting. Thanks.
Yeah.
Yes, a related question. Have you done some ablation studies for both for the bias towards sensitivity and the norm growth? Have you tried some ablation studies to see where does this bias come from?
Can you repeat the first part of the question?
Have you done some evaluation studies? Remove in the learning, in the training of the models, you remove one module or one other, and you see if you have still your bias.
Oh, I see. No, I haven't. So that also sounds interesting, but don't know.
Good. So if we don't have any more questions, I propose we thank again Will and Dana as well for two wonderful presentations. Thank you very much to both of you. And before I let you go, so we will now have the welcome cocktail, which will happen just above us, right? So you can take the stairs either left or right and go up one stair. And yeah, unfortunately, Dana cannot assist with us to the to the welcome cocktail. It will be upstairs. And a few notes about the organization. So not that tomorrow the conference will not be here, right? It will be in Hotel Farah. So today the conference was here in the Faculty of Science, but tomorrow and the remaining days of the conference until Thursday, it will be at Hotel Farah, which is roughly 15 minutes taxi ride from here. You can also get there from using the tram. And I think that's all I had on the logistics side, right? Perfect. So that concludes the day. Thank you everyone for being there. Welcome again to ICGI. And now let's go have some welcoming cocktail upstairs. And bye, Dana. Thanks again. And thanks to everyone online. Have a good end of day. Bye-bye.